Bismillahirrahmanirrahim. ELE424 Analog Electronics 1, Video Pack 3, Video 9. This is the final video under the Video Pack 3 Bipolar Junction Transistors, and also the last subtopic under the AC Small Signal Analysis. So just to recap, under BJT we had the device, and then we had DC biasing circuits, and then the last subtopic was AC Small Signal Analysis, of which there were a few videos covering fixed bias, voltage divider bias, emitter bias, and now we're going to have a look at a miscellaneous of bias, and this video will mostly look at the emitter follower. I am one Fazlida Hanim Abdullah. I'm from the Faculty of Electrical Engineering, UiTM Shah Alam. So we have covered these topics in green, covering AC small signal analysis subtopics. We have done fixed bias, voltage divider bias, and emitter stabilized bias. Now for this slide, we will focus on emitter follower, and we will also cover a little bit of common base and just have a very quick look at collector feedback before we finish off with looking at the effect of RL, load resistance, and RS source resistance. Okay, approach. This is a cut and paste video from the past videos that we have covered. So the approach is the same. We do the AC equivalent circuit, replace it with the RE model, and then we do the circuit analysis to obtain the relevant parameter expressions. Okay, so emitter follower configuration. We have covered emitter follower when we did DC biasing circuit. So what we are going to do now is as what we did with all the other subtopics in AC small signal analysis, is that we are now going to look at the AC equivalent circuit and do the necessary analysis. So just to jog our memory, this was the circuit for emitter follower, but now we have drawn it with the input with the two-port network parameters, current and voltages notation. So when the output is taken from the emitter terminal, the network is referred to as an emitter follower. Okay, this was covered when we did the same thing in DC biasing circuit. Just again, just to jog your memory. So now it is an emitter follower because previously in the other subtopics in AC analysis we took the output from collector. Now we're taking the output from emitter. And the output voltage is always slightly less than the input signal due to VBE drop, but the approximation AV equals to 1 is usually a good one. Okay, so with an emitter follower you expect that the gain is approximately equals to 1. And the fact that V out follows the magnitude of V in with an in-phase relationship accounts for its name, emitter follower. Okay, because it takes it from emitter and it follows V in. Okay, so voltage gain is 1, and that is what we have. So also during AC analysis, collector is grounded. Okay, this part here. So this becomes connected to ground, and that is why this configuration can also be called common collector configuration. So the emitter follower configuration is frequently used for impedance matching purposes, because we said that the gain is 1. So what's the purpose? So it's actually for impedance matching purposes. It presents a high impedance at the input and a low impedance at the output. Okay, the other amplifiers that we have covered have low input impedance and high output impedance, but this one is different. So why do we need something different? Is because when we connect circuit to a load, the impedances of the circuit output, meaning the source, and the load needs to be matched for maximum power transfer. So whatever that you get that you connected here next after the output circuit, it has to match. So if this is low, this has to be low as well. Okay, so so now we know how the circuit looks like. We can draw the equivalent circuit and the RE model. So you have RB, which was connected to VCC, but then it was grounded, so we have a line in the ground. And just like the emitter stabilized bias, there is an RE here. So between emitter and ground there is a resistor. But in the emitter follower circuit there was no RC that we had earlier, so collector is grounded. Okay, the input port parameters are IN, VIN, and ZIN. Okay, just as the cases before, but it goes to it goes to the base. But for the emitter, now the output is taken from the emitter. So V out is not taken from the collector, but it is taken from emitter. So V out is from emitter to ground. I out is the current that goes through RE entering emitter, and Z out is the impedance, output impedance seen looking back at this output port, which is between the emitter and ground. So the AC equivalent circuit now has RE between emitter and ground, okay, just like emitter bias. There is no RC for this particular circuit, as I mentioned just now, and V out must follow the two-port network parameter notation defined earlier. As in AC analysis with emitter stabilized bias, our analysis will be limited to cases where R out can be approximated to open circuit without causing significant difference in results. Remember the emitter stabilized bias, we had we could assume that R out is could be ignored under the assumption that R out is greater or equal to 10 times RC plus RE, and R out is much bigger than the small signal emitter resistance, small signal RE. Okay, and in this case, because RC is equals to 0, so what you have is R out is is equal to greater or equal to 10 times RE only. Okay, so now let's see how to calculate Z in, Z out, and AV. So starting with the input impedance ZE, to find Zin, find equivalent resistance looking into the input port. This is just the same as the emitter stabilized bias, where we do KVL to find ZB, where we treat ZB is the input impedance, and we relate ZB to Vin, where Vin is equals to IBZB. Okay, it's like having this grayed out part of the network to be represented by the equivalent impedance ZB. So this is just a repeat, just so that you know you can visualize this in your mind. So I have Vin equals to IB, because this is the current that goes through the base terminal, and the rest, this read out part of the circuit is represented by ZB here. Okay, so I can do KVL, or I can do Ohm's law, whatever you want to call it, across beta RE and beta RE of the small signal model parameter, and the RE, which is the emitter resistance. So Vn is equals to IB beta RE plus IE RE, because IB goes through beta RE, but IB does not go through RE emitter resistance. For the emitter resistor, what goes through the resistor is the emitter current, IE. Okay, so replacing IE with beta plus 1 IB, which we already know, so whether it is DC value or a small signal AC value is the same. So IE is equals to beta plus 1 IB. So having this expression, we're going to rewrite this equation to be Vin over IB, because what we actually want is ZB, and ZB is beta RE plus beta plus 1 RE. This is the same as emitter stabilized bias, where if you have the values, you can just put in the values there, but if you want to approximate to have an easier equation to carry on, then you know that beta is between 15 to 100, therefore we can say it is much bigger than 1, and we can ignore this effect of 1. So you have ZB is equals to beta small signal RE plus emitter resistance RE, and again we know that RE is in the kilo ohm range, and RE is the small signal model parameter, which is usually less than 50 ohms. So you can actually simplify that further and making it approximately equal to beta times emitter resistance RE. But if you have the value and you want to put it in, that's fine. But even if you do that and you compare between these two, you will find that it's about the same. And why are we finding ZB? Because we know that Zin, which is the input impedance, is RB parallel to ZB. We know how to find Zin. Now let's find Z out. So the strategy with Z out here now is that we would like to simplify this whole network when seen from the output port emitter to the ground. Okay. Initially, when we did emitter stabilized bias, when we set Vin equals to 0, we said that beta IB would be an open circuit. But in this case, it's not going to be so, because under this treatment, IB is not going to be 0. So let's simplify the circuit as seen from the output port. And in order to do that, in order to simplify that, we're still going to set Vin equals to 0 to find Z out. But before we do that, we're going to simplify it. And in order to do that, we need to get a simplified circuit by looking at IB equals to Vin over ZB. Remember, this came from the just the previous slide. Okay, IB is equals to Vin over ZB, and we would like to express this in terms of IE. So IE is equals to beta plus 1 IB, which is going to be beta plus 1 Vin over ZB. Okay, because IB is Vin over ZB. And if I were to rewrite this expression by replacing it with the expression for ZB, I'm going to get IE to be equals to beta plus 1 Vin divided by ZB, which we found earlier before we simplified the expression, was beta RE plus beta plus 1 RE. Now, because we know that beta plus 1 is approximately equals to beta, because beta is large and the effect of 1 can be ignored, so we can actually cancel beta from the numerator and denominator, and we have this expression of IE equals to Vin divided by small signal RE plus emitter resistor RE. Okay, again, please don't say 2RE here, because these are two separate resistance. The small RE is a small signal RE, and the big RE here is the emitter resistor. So we can now redraw this expression by doing a simple circuit here consisting of Vin, the small signal RE, and the emitter resistor RE, where we get this expression for IE by just saying that this is like a simple voltage source and resistor network. Okay, and we do KVL around here. I get minus Vin is equals to IE RE plus IE small signal RE plus IE times emitter resistor RE. Okay. Now, why do I want to have it simplified here? Again, remember, to set to find Z out, we set Vin equals to 0. So now when we set Vin equals to 0, we don't have any other networks that would make our equivalent resistance difficult to find. So if Vin is set to 0, what I have is the small signal parameter RE in parallel with the emitter resistor RE. Okay, so now how do I find AV, voltage gain? Using voltage divider rule, now because we have simplified the circuit, okay, using voltage divider rule on the circuit that was simplified as seen from the output port, I can find an expression of V out relating to Vin by using voltage divider rule, where V out is equal to RE divided by emitter resistor RE divided emitter resistor total resistance and small signal RE times Vin. So rearranging, I can find the expression V out over Vin, which is equal to emitter resistor RE divided by emitter resistor plus small signal parameter RE. And if we want to further simplify it, because we know that RE emitter resistor is in the kilo ohm range, and a small signal parameter is usually around 10 to 50 ohms, so we can say that it is approximately equals to RE emitter resistor. Therefore, V out over Vin is equals to, you can simplify this, and it is approximately equals to 1. Which means this is what we mentioned earlier. This is an emitter follower where V out is equals to Vin, and the sign is positive. Okay, so V out and Vin are in phase for the emitter follower configuration. So now let's do an example. In this example, we are given an emitter follower configuration. We need to find a small signal parameter RE, and followed by the two-port network parameters Z in, Z out, and AV. Okay, so this is just demonstrating the amount of thought involved. It's not that difficult. It's just the same as the rest, except that the approach here, the only difference is that the approach here is that when you want to find Z in and Z out, you need to use the concept of IB equals to V in divided by ZB. Okay, so this is DC, this is finding Z in, this is finding Z out, and this is finding AV. So that we can see that what was written clearer. For the DC analysis, okay, we have RB and RE, so let's consider the input loop, and just using the simple concept of total voltage drop. Okay, you find VCC, the whole of VCC here would be equals to the voltage drop across RB plus the voltage drop across base and emitter and the voltage drop across RE. So VCC is equals to IBRB plus VBE plus IERE. Okay, where we know that IE is beta plus 1 IB. So rearranging, we find IB is equals to 20.42 microamps. Okay, and IE from beta plus 1 IB is equals to 2.062 milliamps. And we can find the model parameter RE equals to 12.61 ohms. So now with this value of RE, we are ready to leave the world of DC analysis. We are now going to enter AC analysis. This is our AC equivalent circuit with the coupling capacitors shorted, okay, and output taken from the emitter terminal with the BJT replaced with an RE model of beta RE and IB beta IB. Okay, so beta RE is 12.61 kilo ohms. To find V in, this is just the handwritten version of what was given on the slides a few slides before. Okay, just to show that it's the thought that is involved is not difficult. Is just that it's looking at it from a different point of view. Okay, where now to find Z in, we need to find ZB, and ZB is equals to V in over IB. So to find ZB, we just need to consider at the branch between base to ground that goes through emitter. So V in is equals to IB beta RE plus IERE. You have to refer to the small signal model, and replacing IE to be equals to beta plus 1 IB. So having an expression of V in and IB only, I can rearrange to write V in over IB, and I get this expression beta RE plus beta plus 1 RE for ZB. So replacing the value of beta, which is equals to 100, RE, which is equals to 12.61, which we found from DC analysis, and RE from the value that is given, which is 3.3 kilo ohm, we find that ZB is 334.56 kilo ohm. Okay, so why do we find this value of ZB equals to 334.56 kilo ohm? That's because we want to find the input impedance, and input impedance is RB in parallel with ZB, giving us 220 kilo ohms, that is parallel to 334.56 kilo ohm, equals to 132.72 kilo ohms. Now compare this with the configurations that we had before this. Okay, you will find that with this emitter follower configuration, we have high input impedance. This is in the kilo ohm region, 100 of kilo ohm region. Okay, now to find Z out, we will have to find the simplified version. And to find the simplified version, we start with IB equals to V in over ZB again. Okay, we want to simplify it so that we can set V in equals to 0 to find Z out. Okay, so knowing V in IB is equals to V in over ZB, and IE is equals to beta plus 1 IB, we find an expression for IE which consists of beta once approximated, we can cancel the beta from the top and bottom, and we have an expression of IE is equals to V in over small signal RE plus emitter resistor RE. And based on this expression, we can draw this representation, okay, which consists of voltage V in and IE going through small signal RE and going through emitter resistance RE, capital RE. So this has simplified, gives a simplified representation of the circuit that we had before, and here we can set V in equals to 0 to find Z out. So which would give us, if this is 0, I'll have small signal RE in parallel with capital RE, which would give me 12.61 ohms parallel to 3.3 kilo ohm, which is about 12.56 ohm. And again, compared to the examples that we had and the configurations that we had before this, okay, Z out is much lower. So this is demonstrating the fact that emitter follower has low output impedance instead of high output impedance. And to find AV, we'll be using this simplified network. Okay, and from that simplified network, we do a voltage divider rule. Okay, find V out over V in from voltage divider rule on the simplified network representation. Okay, so VDR, we have V out is equals to emitter resistance RE divided by the total resistance in the simplified network times V in. So what we want is actually just an expression of V out over V in, and we are going to find this to be approximately equal to 0.996, and this is approximately equals to 1, which is again emphasizing the fact that for an emitter follower, demonstrating the fact that emitter follower has the V out following V in terms of magnitude as well as phase. Okay, now what we can demonstrate the effect of R out. We're not going to do the working here. You can refer this to the textbook. But to demonstrate effect of R out that does not satisfy condition to be ignored, i.e., what happens if R out is not greater than 10 RE? What happens if the assumption is not valid, it's not met? So let's consider an example that was the example that just now that we just did. What happens if R out is, let's say, 25 kilo ohms, and 25 kilo ohms is not bigger than 10 RE? So based on this calculation, you still get AV about the same, okay, which matches the earlier result. So if R out were to be 25 kilo ohms instead of approaching infinity, Zin would be 126.15 kilo ohm instead of 132 kilo ohm. Z out would still be 12.56, and voltage gain would still be 0.996, which is close to 1. So what we can show here is that what is being demonstrated here is that for most applications, a good approximation for the actual results can be obtained by simply ignoring the effects of R out for this configuration of emitter follower. Okay, now what happens if your emitter follower have some modifications to the biasing circuit of the emitter follower as shown? Because the emitter follower that was analyzed just now only had RB. What happens if RB is a combination of R1 and R2, like a voltage divider, like this? Okay, so presence of R1 and R2 will only change expressions that include RB, and that expression will just be replaced by R1 and R2. It doesn't actually change the expressions for Z in, Z out, and AV significantly. And what happens if there is an RC here? Okay, again, presence of RC will not affect expressions of input impedance Z in and output impedance Z out because it is not reflected into the base or emitter equivalent networks. Now, the presence of RC again will only change the Q point but not the voltage gain. So we'll leave emitter follower. We will now look at common base configuration. The common base configuration, okay, now the circuit is going to be something else. We have left emitter follower. With the common base configuration, the base will be connected to ground, and input will be fed through emitter, and output will be taken at the collector. So the common base configuration is characterized as having relatively low input impedance and a high output impedance and a current gain less than 1. So which configuration do you take? It depends. If you're building a circuit and you need to build an amplifier, it depends on your requirements. In this case, the current gain is less than 1, but the voltage gain, however, can be quite large. So we can draw the AC equivalent circuit, and with this common base circuit, we need to use the common base configuration of RE model. Please refer to the slides under the subtopic of AC model. Okay, so in this case, Zin is a simple equivalent resistance of emitter resistor Re and small signal model parameter Re. Okay, and Zout is equal to Rc. For AV, okay, AV is going to be again the same approach that we take. We do an Ohm's law at the output port, so we have V out is equals to negative I out Rc, negative because I out enters the negative terminal, and in this case our expression here will be in terms of IE. Okay, so we need another expression that contains IE, relating IE to Vin. So this is at the input port, we have Vin is equals to IERE. Replacing that, we will find AV to be equal to RC over RE. And for the current gain, okay, current gain is I out over I in. Okay, and I in is IE, and I out is negative alpha IE, and it's going to be about equals to negative alpha, which is about negative 1. So this is the common base. Let's do an example. For the example, I have not done the written version. It's quite simple here if you need to do it, because the finding of Zin and Zout is quite straightforward because of the configuration. Okay, so you can have a look at this. And the last configuration that we will look at is the collector feedback. Now for the collector feedback configuration, what I'm going to do is I'm not going to go through any of the examples. It's just to show that if we have this circuit, we did the circuit when we did DC biasing. Okay, we can still draw the AC equivalent circuit, okay, and replace this with the RE model. But now between base and collector, you have the feedback resistance RF. Okay, or if you have a capacitance connected between RF1 and RF2, separating it, one RF, okay, because it goes to ground, one RF would be separated, goes to the input network, and the other RF, which is connected to the collector, is joined to the output network. Okay, so I'm not going to go into the collector feedback circuit. You can have a look in the textbook just to have to close the loop on the collector feedback, because we covered this in the DC biasing. Alright, now we have covered all the configuration. Now before we finish on the AC analysis, let's have a look at effect of RL and RS. So what are we actually talking about here? All the parameters determined in the last few sections have been for an unloaded amplifier. We talked about input impedance and output impedance and it having a load, okay, but we did not consider any of the load resistance that is connected to the output port. So we have been considering unloaded amplifier with the input voltage connected directly to a terminal of the transistor without considering source resistance as well. So there will be effects when we apply a load to the output terminal and the effect of using source with internal resistance. So this is what we have. We have only considered this BJT amplifier without any load and without any source resistance. We assumed a no load condition. But here we want to have a look what happens when we take this amplifier, because when we design an amplifier, obviously we need to connect it to an input, to a source circuit providing the input signal, and from the amplifier as well we want to drive something else, so we need to connect it to the load resistance. Okay, so we will compare three cases: no load, that is when we just design the BJT amplifier, and then with load resistance, and finally with load resistance, this is the load resistance, and then finally with load and source resistance, RL and RS. Okay, so when we did our analysis for all the subtopics before this, okay, we assume there is no load, so V out is just taken at the output terminal after the coupling capacitor, and V in is taken again at the input terminal before the coupling capacitor. So our AV, voltage gain at no load, AV and L here, is V out over V in. Okay. Now if there is a load resistance, our V out here would include RL. So it's still V out over V in, okay, still V out over V in, but V out is taken across RL. And if we have a source resistance, here we will label this as AVS, okay, and it will be V out over VS, because it includes VS here when we have both RL and RS. So AVL refers to no load gain, AVNL refers to no load gain, AVL refers to when there is load resistance, and AVS refers to when there is load resistance as well as source resistance. And for the same configuration, we will find that the gain for the no load is going to be the greatest, but once you connect it to a load, there will be a reduction in gain, and when you connect it to a source input, to an actual hardware source connection here, the gain will again further be lowered. So let's see why that happens. So okay, again with the formulation with an AC equivalent circuit, okay, before this we did not have RL and we did not have RS. So what's going to happen if we have RL and RS? Now let's first look at the effect of RL. With RL, that means our output resistance at the output part, okay, is going to be R out parallel to RC parallel to RL. Okay, for example, because if there had been no RL, it would just be RC and R out, but because there is an RL, now it becomes it has to be considered. Okay, and when we do expression for voltage gain, for example, for this AC equivalent circuit, we're going to have to consider V out, which is equals to minus beta IB going into the equivalent resistance of all this resistance. Okay, and replacing IB with the input section of V in equals to beta RE, we'll have an expression of V out and V in, which is going to be equals to RC parallel R out, assuming that here we are ignoring R out, okay, R out output resistance here, but the combination of these three resistance here will be RC divided by RL, okay, collector resistance parallel to the load resistance, divided by the small signal parameter RE. We also know that when we have two parallel resistors, the equivalent resistor of the two parallel resistors will always be smaller than the smallest resistor of the two. So this effectively shows that the voltage gain with a load will be reduced because of the presence of a load resistance. So now what happens if there is a source resistance? If there is a source resistance, okay, I can do a voltage divider rule across the input impedance of all this network as represented by Zin. So I have Vin is equals to Zin divided by Zin plus Rs times the source voltage Vs. Okay, so I can express Vin over Vs, and then instead of because when we want to find a voltage gain, it will have to be V out, and the voltage gain for amplifier with the source and load resistance will be V out over Vs. So because we already know V out over Vn with the load, so it's V out over Vn with the load times Vin over Vs, and Vin over Vs here will be a value that is less than what it was, meaning that this value will always be less than AVL, because this value here is going to be less than 1. Okay, because it's, you have Zin over Zin plus Rs. If Rs is 0, then you can say that AVS is equal to AVL. But if there is a source resistance, then this value will indicate that it's always going to be less than the voltage gain with the load. So for a particular design, the larger the level of RL, the greater is the level of AC gain. So what does that mean? We know that RL, for whatever value it is, okay, the larger value of RL, you're going to get RC parallel to RL closer to RC, which is to the no load gain. Okay, so the bigger RL is it, the bigger the voltage with load is going to be. But this voltage with load will always still be less than the no load gain. Okay, but to be closer to the no load gain, it would be better if RL is bigger. Also, AVS obtained with RS, okay, this was an expression that we had from the previous slide, will always be less than AVL. AVS will always be less than AVL due to the drop in applied voltage across RS. And for a particular amplifier, the smaller the internal resistance of the signal source, okay, the smaller RS is, that is better for the overall gain. So for a good gain of the amplifier, it is good to have small RS and big RL. Also, for any network that have coupling capacitors, okay, these are the coupling capacitors, RS and RL do not affect the DC biasing levels, because the coupling capacitor would have isolated the DC values before and after the amplifier. Okay, so the Q point, meaning the Q point of the transistor, is solely because of the DC biasing circuit, because the coupling capacitors have successfully shut out the DC influences at the input and the output terminals. So when one builds or purchases a packaged amplifier, the listed gain or the expected gain, the calculated gain, and all of the parameters are for unloaded situation. So the gain that results due to the application of RL and RS, because when you build an amplifier, you want it to be connected to a source module and driving a load module. With RL and RS, it can have a dramatic effect on all the amplifier parameters, which you would should be prepared to consider. So demonstrating effect of RL and RS, we're going to do an example, and with this example we're going to take an example of a fixed bias configuration that we did earlier, okay, when we did fixed bias AC. But now we're going to connect it with an applied load of 4.7 kilo ohms here and a source resistance of 0.3 kilo ohms, and we want to determine the following values compared to the no load values. First, the voltage gain just with the load, and then the voltage gain with load and source, and we're going to have a look at the input impedance and output impedance. Now this is from the textbook, you can have better read there. So this is a copy and paste from the fixed bias part. Okay, so this is DC and AC analysis without RL and RS from fixed bias past example. So here you have a gain of negative 280.11. Okay, I'm not going to go through this, we've gone through this, you can have a look from previous slides. So the solution is, if we have a load resistance of 4.7 kilo ohm, the gain now will be reduced from negative 280 to negative 170.98, and this is significantly less than the no load gain. But if you have a source resistance, it will further be reduced from negative 170.98 to this value using the expression for AVS, which will give us negative 133.133.54. Okay, and if we compare, the input impedance is the same, okay, which is 1.07 kilo ohms, and the output impedance is also the same, which is 3 kilo ohms. Now I have not shown any of the work here. You should do this on paper yourself to demonstrate that this is the workings that are involved. Alright, so this is the end of AC analysis of BJT single stage amplifiers. We have covered all subtopics: fixed bias, voltage divider bias, emitter follower, and we had a quick look at the other amplifiers configuration. This is the end of AC analysis, and this is the end of BJT topics, which we cover in this course. You will see more of BJT in future courses that you will be taking. Okay, but in ELE424, our next main topic is the metal oxide field effect transistor, MOSFET. Now, MOSFETs are the most widely manufactured device in history. Okay, between 1960 to 2018, there are more than 10 to the power of 22 MOSFETs that have been manufactured, and that is more than 90% of all transistors in the world, including BJT. Okay, so we'll have a look at MOSFETs in the next video pack, which is video pack 4. I'll see you in the next video. Thank you. Assalamualaikum.